Good evening. Today I want to share with you my research, ProtoEvolve. ProtoEvolve is an evolutionary approach to solving supply chain execution problems using large language models. And my name is Guru Rangavittal. I am a DTech candidate, and I would like to use this time to kind of share the details behind my research. The inspiration for ProtoEvolve came from a research paper that Google DeepMind published in 2025 called Alpha Evolve. Alpha Evolve uses evolutionary approaches as well as large language models to solve business problems. They frame any problem in the form of a code, and then through continuous improvement of the code, they're able to improve on the solution to a given problem. And the applications of Alpha Evolve are manifold. You can use Alpha Evolve in many planning kind of scenarios. You can use Alpha Evolve to solve science problems. You can come up with new algorithms and new solutions to problems as well. Now, we are going to be leveraging Alpha Evolve as an inspiration, but we're also going to go into where Alpha Evolve really has some challenges. And so we're going to be touching on how we are going to overcome some of these challenges in our discussion today. So, firstly, what problem are we trying to solve? We are trying to look at any kind of a supply chain execution problem. To give you an example of a supply chain execution problem, imagine a shipment that is need to be delivered, and let's say this shipment requires a refrigeration, and this refrigeration can, let's say, has a risk of breaking at any point in time. Let's say if it does happen that maybe there is a problem in the refrigeration, and then you have to react to these events that happen in real time. Somebody has to either determine, is this a real problem, and so if it's a real problem, do we need to reroute the shipment, and you need to come up with an alternative route for a given shipment. And so that you want to make sure, first and foremost, your customer experience is not impacted, the cost is also low. At the same time, you want to reduce the deviation and overall time taken to deliver the particular shipment. And you have to do all of this in real time. So the time it takes for you to decide is going to be critical here. We are solving this problem today in many ways. First and foremost, humans solve this problem. A human decision maker might take a call as to how a particular shipment needs to be routed, or sometimes you have deterministic systems solving this problem. But first and foremost, you need to have visibility. But visibility alone is not enough. You also need to be able to react in real time, or else the downside of not being able to react in real time could be significant loss of inventory, because let's say you're transporting something that requires a specific temperature. If that temperature is violated, then it kind of reduces the shelf life of that particular product. So yeah, that's really the problem that we are trying to tackle. And as I mentioned before, humans can be used to solve this problem, or alternatively, you could use some systems. And earlier we used to have very deterministic systems that use traditional heuristics. This kind of a rerouting problem is a very well known problem. It's called the capacitated vehicle routing problem. And we have algorithms that are already well established, like the clock ride algorithms. Very traditional heuristics are available, but then they are not very agile in terms of being able to incorporate some of the volatility in the real world. And so they are fairly static and not very helpful. Let's say when there is a weather situation, when there is a lane closure and things like that, some of these very traditional heuristics really fall flat. Now that's where solutions like Alpha Evolve and even the later version called Deep Evolve have a good handle on being able to adapt to some of these changes in the environment. And the only challenge that we have in some of these evolutionary approaches is the time it takes for these evolutionary algorithms to execute. Sometimes it could be hours, it could take quite a significant amount of time for some of these algorithms to run. So they may not be really good candidates when we are looking at execution kind of problems, where you really need to have solutions that can be solved in a few seconds, or at the worst case some in minutes, so that you can react to some of these real-time events, and make the right decisions. And that's where ProtoEvolve identifies an architecture that will help execute in real time. At the same time, take advantage of some of the power of evolutionary algorithms and large language models. So it brings the best of both in terms of leveraging the evolutionary algorithms and large language models. At the same time, has an architecture that allows it to react pretty much in real time and makes it a lot more agile. And this slide really is a depiction of what is the role of the human. The role of the human in the world before was a lot of cognitive overload. While we had a very passive digital twin of the of the supply chain of the model in the past, that still left a lot of decision dependent on humans, and the decision time could take hours. So first and foremost, you have an opportunity for things to go bad. Number two, it's a significant load on the humans. But the solutions like ProtoEvolve really allows a lot more autonomous agentic execution, thereby elevating the human into a lot more managerial role, being able to look at an overall outcome, and leveraging the agents and autonomous capabilities to execute a lot better. And so that really makes the human life a lot more easier. And so how is ProtoEvolve able to achieve this kind of a lower latency? And part of the way ProtoEvolve is able to solve this problem better is through what is called as a map elites approach, where you're first and foremost defining dissecting the whole problem into smaller problems, and then once you have identified smaller problems of the bigger problem, you can solve each of the smaller problems independent of the bigger problem. I mean, independent of all other problems, so that now you have a good solution, the best solution for each of the smaller buckets of problems. So let's look at this particular problem. In this case, let's say the refrigeration unit failed. The refrigeration unit failure could be of different classification. You could have a 0 to 2.5 degree centigrade failure, or you could have a 2.5 to 8.5 degree centigrade failure, or it could be much worse, where the whole refrigeration unit collapsed. Now, those could be the kind of problems you're looking at. At the same time, you could also be looking at different scenarios. Let's say you have one scenario where you have only one depot that can pick up and you can deliver to customers, or you could have two depots. So you have the ability to, let's say, operate with a much more variety of logistic constraints. And then you could have multiple depots, so where you have a lot more variables available for you to identify the best possible route for your given shipment. So you could dissect the problem into smaller problems, and then you can define the best solution within each category. And for defining the best solution in each category, you could apply multiple goals. For example, you want to make sure that the cost is low. You want to make sure that the time taken is low. You want to make sure that the customer experience is not impacted. So as you establish the criterion for defining the best solution within a smaller bucket, you could have a multi-objective formula, like as it mentions here, mu1 times delta cost, mu2 times delta latency, mu3 times safety margin. You have to come up with a score to identify which is the best solution within a given bucket, and then you can bubble up that solution and keep it ready, so that as and when you know the bucket that you are looking at, you can immediately pick up the best solution from that bucket and then you start using it. So that's what allows you to reduce the latency of execution, so that many of these solutions are pre-computed and made available, and so you don't really run it in real time, but you solve it ahead of time, and then you're able to take it, use it even in execution problems. That's really the fundamental difference that ProtoEvolve brings over Alpha Evolve and Deep Evolve. And okay, how are we going to establish this through an agentic implementation? So for this, we are looking at three different types of agents. One agent which will have a model of the supply chain. In this case, let's say a domain knowledge graph where you have nodes which are really the uh, actual supply chain locations, and then the edges could be the lanes. And now the agent has an access to the knowledge graph and calculate the cost, calculate the total time taken, calculate the risk to the customer. All of that will be handled by one agent. And then the other agent will take advantage of this agent and then define which code is the best code given these constraints. And in order to make sure that the code is not completely, moving against guardrails, it establishes what is called as an abstract syntax tree, which really defines the template that the code needs to follow, so that the code is generated in a fairly well-defined and is not a significantly variant mutant compared to the rest of the compared to what is expected for that code. And finally, the auditor agent will be the one which will determine which of the code is the best code. And so that could be a deep reasoning model. You could have a Gemma 2B for the generator, Gemini Pro for the auditor, so that you can identify the best code for a given bucket. And so what is the architecture? The architecture that we are looking at is a simple architecture where you have some ingestion layer which brings in all the telemetry, the IoT data or the signals from the transportation system or the enterprise system, and then bringing into the agentic layer, which is a multi-agent collaboration, which will define what is the scenario that we are trying to tackle, and then which will pull the best solution among the different buckets, and then it will pass it on to the next layer for execution and evaluation. And then at the execution layer, you identify the total cost, the total time taken, as well as the risk to the customer, and then you start defining what is the business outcome. And in all of this process, the human really operates as somebody who oversees the execution. And the basic goal for this entire architecture is to eliminate decision latency, so that we are able to improve on the key metrics, whether it is route accuracy, whether it is service level, or whether it is reduction in spoilage. All of those parameters are measured and then identified used to identify which is the best solution for the given scenario that we are coming up with. So how do we validate? So the way we are going to validate this is through ANOVA and 2-keys HSD. At this point in time, we are going to be doing some simulation trials, but we could be using some real-time, real-life data for doing this evaluation. The core data set that we are looking at for the simulation is the Solomon CVRP and IoT data. We could also be taking this and evaluating it with an enterprise with real data as well. And from an operational metrics perspective, as I mentioned before, we could be looking at some of the key metrics like spoilage, the route accuracy, the overall compilation success rate of the code, so that we know that every solution that we are generating is feasible. And then from a statistical proof perspective, we will be using ANOVA to make sure that at least one solution, among the different options we are evaluating. The different options we are evaluating could be like number one, the ProtoEvolve solution. Number two could be the Alpha Evolve / Deep Evolve solution. Or number three could be the human triaging solution. And we want to make sure that ANOVA is able to establish that at least one solution is better. And then the 2-keys HSD can establish that the ProtoEvolve solution is better than the human triaging, ProtoEvolve is better than Alpha Evolve and Deep Evolve. And so we are able to use this kind of a framework to validate our solution. Now, I'll quickly switch over to the simulation, and just to give you a little feel for how we are thinking about this. As I mentioned before, the metrics that we are measuring are going to be the latency, the spoilage, the route accuracy, as well as the feasibility of the solution. That's what is captured by the AST compilation, which is really whether the solution is feasible to implement. And then from a selection of the solution, here is the bucketized grouping of the different options, different scenarios. On the y-axis, you can see, we are grouping it by the gradient of temperatures 0 to 2.5, 2.5 to 8 degrees centigrade, catastrophic blockage versus a complete failure of refrigeration unit. And then for the different scenarios, we are looking at, let's say, one depot or a two depot or a multi-depot scenario. And you can actually see the kind of options we are seeing. For example, this is the three depot scenario with a moderate failure, and you can actually see that the tool is able to generate solutions for a three depot scenario. And then you can actually see that the code is also readily available for us to start using immediately. As and when we define what is the scenario, what is the severity of the issue, we can immediately go and pick up the best solution, which is already available here, and then start using for identifying what is the route that the shipment needs to take. And in order for evaluating the statistical performance, you have the ANOVA variance test, and you can actually see that the F statistics is quite high, which means that there's definitely a significant variance among these different solutions. And then you can also see that the ProtoEvolve solution is better than all the other solutions. ProtoEvolve over human, ProtoEvolve over AlphaEvolve and DeepEvolve really has quite a high significance, so that we know that ProtoEvolve is performing better. And across the different metrics also, we notice that ProtoEvolve has a much better performance compared to the manual human triaging, as well as AlphaEvolve and DeepEvolve. So that's a quick simulation of our approach. And then to wrap it up, from an impact perspective, you can see that the ProtoEvolve is able to reduce the total decision time from hours to less than 60 seconds. ProtoEvolve can also ensure that there is capital efficiency. You don't need to refactor your existing ERP or a TMS architecture in order to leverage the significant merits that ProtoEvolve offers. As well as from a quantitative impact perspective, you can see that ProtoEvolve first and foremost lowers the spoilage, maybe even close to 80%, and the feasibility of the solution is almost like 99.8% success. So each of the route that ProtoEvolve publishes is going to be viable. As well as from an execution risk perspective, you are not having to wait for significant long time, which was one of the risks that we noticed with AlphaEvolve. ProtoEvolve will be able to eliminate that risk, or even at least lower the risk, because of the abstract syntax tree approach that we are adopting. So overall, the ProtoEvolve we think is a much better solution for solving supply chain execution problems. We are excited and hope to take this up as part of our research dissertation. Thank you for your attention, and look forward to hearing your feedback on this.